So earlier we have discussed about improper integral of first kind and its test for convergency of first kind. So now I am going to start improper integral of second kind. Okay. So what is definition of improper integral of second kind? So as we have an integral a to b fx dx is called improper integral of second kind if lower limit a or upper limit b or both the limits are finite. Okay, both the limits are finite, but in this region or this limits or between the limits this function is unbounded. In other words, lower limit or upper limit are singularities of the given function. So this integral is called improper integral of second kind. So this is the difference, means if limits are infinite or finite. So in the case of infinite limit, I have discussed improper integral of first kind. But if limit are finite but function is unbounded at that limit, so this is second kind. So how we define improper integral of second kind? So now if an integral a to b fx dx is of second kind and point A is a singular point, so a to b fx dx is equal to limit t tends to 0 a plus t to b integral of fx dx. Okay, and similarly if b is a singular point, then we can define a to b fx dx equal to limit t tends to 0 a to b minus t fx dx. Okay, here we see that this point t lies between open interval a to b. Okay, so since in open interval end points not included, so when we calculate first limit, so here we put a plus t, and when we calculate last, means b is not included, so when t tends to 0, so here we take b minus t. Okay, so this is the definition. Now if a given function is unbounded in the both the limits, so we can divide into two parts. Okay, so a to b fx dx is equal to a to c fx dx plus c to b, where c lying between a and b. Okay, so how we can test this integral is convergent? So in all the cases, if right hand side, we calculate right hand side first, second and third. Okay, so if all the cases we get finite value of the given integral, so we say the given integral is convergent. Okay, so now some examples of improper integral of second kind. Okay, so there are some examples. First is 0 to 1 dx upon x square. Second is 0 to 1 dx upon square root 1 minus x. And third one is 0 to 2 dx upon 2x minus x square. So first we see very carefully these examples. So first is there is lower limit and this is upper limit and this is function. So here if x is equal to 0, so this function goes to infinite, means lower limit is a singular point of this function. Okay, so how we calculate this improper integral of second kind? Okay, so this is the solution, means by the definition dx upon x square equal to limit t tends to 0. Some authors also denoted by some lambda or epsilon in place of t. So this is same thing. So we can write also t plus plus 0 here. So integral t to 1 dx upon x square. So this integral is very easy because this is standard form, formula x to the power n dx. So here in place of here n is minus 2. Okay, so this equal to limit t tends to 0, 1 upon x with negative sign, t to 1. So this equal to limit t tends to 0, upper limit 1, so here minus 1 and minus 1 is plus 1 upon t. Okay, and taking limit, so t equal to 0, 1 upon 0 infinite, so minus 1 plus infinity is equal to infinity. Since this value is equal to infinite, means limit does not exist, therefore given improper integral is divergent. Okay, so this is the solution of this equation, this question. Okay, now second question is 0 to 1 dx upon 1 minus x. Okay, so here upper limit 1, if we put 1 minus 1 is equal to 0, means 1 is a singular point. Okay, so by definition limit t tends to 0, integral 0 to 1 minus t dx upon 1 minus x. Okay, so again this is t tends to 0. So here if we put 1 minus x is equal to capital X, so dx is equal to minus dx. So this is again in standard form. So dx upon x to the power half, again the formula x to the power n dx. So we get the integration to 1 minus x. Okay, 0 to 1 minus t. Now we put upper limit and then lower limit. So upper limit 1 minus t, so minus 2, 1 minus t, this thing, minus 0. So here we put 0, so minus, again minus plus 2. Okay, so now putting t equal to 0 means I am taking limit, so this should be 0, 1 minus 1, 0. So this first part is 0, so we get 2. Okay, so here we get a finite value. So first given integral is convergent. So by definition we can easily calculate given problem. So first we check the given integral is first kind or second kind. So if limit is finite and function is unbounded at that limit, so given function is improper integral of second kind. So by the definition we can calculate very easily. Okay, it is clear. Now the third problem is integral 0 to 2 dx upon 2x minus x square. Okay, so this can be written as 0 to 2 dx upon, here x is common, 2 minus x. So here if we put x is equal to 0, then 0 is a singular point, and similarly x is equal to 2, then 2 is a singular point. Okay, so lower limit and upper limit both are singular point. So in this case we write here 0 to 1 dx upon x 2 minus x plus 1 to 2 dx upon x 2 minus x. So we divide in two parts, because if both the limits are singular point, then we divide in two parts. So here 0 to 2 equal to 0 to 1 plus 1 to 2, where 1 lying between 0 to 2. Okay, so this equal to limit t tends to 0 plus t to 1 dx upon x 2 minus x plus limit t tends to 1 to 2 minus t dx upon 2 minus x into x. Okay, so here it is clear that this integration is common. So by partial fraction we solve by partial fraction. So since 1 upon x 2 minus x equal to, okay, so for first x, so x equal to 0 here, so into 2 and 2 minus x is equal to 2, so here we put 2, so this is 2 1. Okay, so integration of this thing, because this is common, so integration of dx upon x 2 minus x equal to integration dx upon 2x plus integration dx upon 2 into 2 minus x. Okay, so this equal to 1 by 2 log x minus 1 by 2 log 2 minus x. In other words, 1 by 2 log 2 minus x upon x. So here this should equal to, this is equal 1 by 2 limit t tends to 0 log 2 minus x upon x t to 1 plus limit t tends to 0 log 2 minus x upon x 1 to 2 minus t. Okay, so first we put upper limit and then lower limit. So 1 by 2, upper limit 1, so 2 minus 1 1 and again 1, so log 1. Okay, and minus t, so 2 minus t upon t, and similarly if we put 2 minus t here and minus lower limit, so we get here limit t tends to 0 log 2 minus t upon t, because log 1 is equal to 0, plus limit t tends to 0 log 2 minus t upon t. So this is same thing, so 2 times, so 2 to cancel, equal to limit t tends to 0 log 2 minus t by t. So on taking limit, this should be infinite, so given integral is divergent. Okay, so this is the answer. So now if we have problem to integrate the above integrals, then how we can test whether given improper integral of second kind is convergent or divergent? For the convergency of improper integral of second kind, we shall use the following tests. Okay, so there are 5 tests as we have studied in previous for improper integral of first kind. So in a similar fashion here, same test. One is this thing a to b dx upon x minus a to the power n. Second is the mu test. Third is comparison test. Fourth is Abel's test, and last one is Dirichlet test. Okay, so tests are same but results are opposite. Means when we take first test, so the integral a to b dx upon x minus a to the power n, so this is convergent if n less than 1 and is divergent if n greater or equal to 1. Okay, in the improper integral of first kind, this was just opposite, means that was convergent when n greater than 1 and divergent for n less or equal to 1. But in improper integral of second kind, this is n less than 1 convergent and n greater or equal to 1 divergent. Okay, so this is for singular point of A. When singular point is B, then this can be written as a to b dx upon b minus x to the power n, and result is same. Okay, when n is less than 1 then convergent and n greater or equal to 1 then divergent. Now mu test. The mu test is also similar. So if A is singular point, then integral a to b of x dx is convergent if mu less than 1 and divergent if mu greater or equal to 1, provided this limit x tends to 0, x minus a to the power mu fx exists. Okay, so this is the mu test. And similarly, if b is singular point, so here x tends to b and here b minus x to the power mu fx exists. Okay, so similarly, if b is a singular point, then a to b of x dx is convergent if mu less than 1 and divergent if mu greater or equal to 1, provided this limit exists. Okay, so there is a problem, means how we calculate mu. So mu is equal to power of factor of singular point. Okay, so for example, a to b dx upon x minus a to the power k and b minus x to the power m. Okay, so this is a improper integral of second kind. Here both limits are singular points. Okay, so we can divide in two parts. So in this case, this should be a to c this thing plus c to b this thing, where b lies between a and c. So here we calculate the value of mu. So here x minus a to the power k and here x minus a to the power k. So here a is singular point, so mu is equal to k, and here b is singular point, so mu is equal to m. Okay, so by this method we calculate the value of mu. Okay, so this is an example for mu test. So this is a to b dx upon x minus a b minus x, and second is this thing. So for first, so here a and b both are singular point. So first we write a to b dx upon x minus a b minus x equal to a to c dx upon x minus a b minus x plus c to b dx upon x minus a b minus x. Okay, so this is first and this is second. So firstly we solve first integral. Okay, so this is a to c dx upon x minus a and b minus x. So here x is equal to a is a singular point. Okay, so by mu test, here it is very easy to see mu is equal to 1. Mu is equal to 1 because x is equal to a is a singular point, so mu is equal to 1. So by mu test, limit x tends to a plus 0, x minus a to the power mu is nothing but 1, mu e of x. Okay, equal to limit x tends to a plus 0, x minus a upon fx is this thing is fx, so x minus a b minus x. So this should be cancelled. Okay, so on taking limit 1 upon b minus a, this is not equal to 0 and finite. So for mu is equal to 1, by mu test this integral is divergent. Since mu is equal to 1, therefore this integral is divergent. And similarly, we solve for second case. In second integral is equal to c to b dx upon x minus a into b minus x. Okay, so here b is similar point, so here b minus x to the power half, so here mu is equal to half. Okay, and by the same method we calculate limit x tends to b minus 0, b minus x to the power mu f x equal to limit x tends to b minus x to the power half, and fx is x minus a b minus x. So this should be cancelled. On taking limit, so this is 1 upon b minus a. This is finite, and here mu is equal to half. So by mu test, if mu less than 1, then given integral is convergent. So this is convergent. So here first integral is divergent and second is convergent. So total is divergent. So answer is divergent. What is answer? Answer is divergent. Okay. Now the next problem is 0 से 2 log x upon 2 minus x dx. Okay. So here if we put x is equal to 0, so log 0 is equal to minus infinity. So 0 is a singular point, and when x is equal to 2, so by denominator since 0, so again 2 is a singular point. So we can divide in two parts. So this is 0 to 1 and 1 to 2. Also we can write 0 to a and a to 2, where a lies between 0 to 2. Okay, so this is first and this is second. So in first case, x is equal to 0 is singular point, so first equal to 0 to a log x upon 2 minus x dx. So I want to apply mu test. Okay, so limit x tends to 0 x to the power mu fx equal to limit x tends to 0 x to the power mu log x upon 2 minus x. So since here root 2 minus x, so if we put here x is equal to half, then this should be 0. Okay, otherwise there is a problem to calculate the value of limit, because here log x, so here value of mu lies between 0 and 1. Okay, then this will finite. Okay, so in this case, since mu less than 0, mu less than 1, therefore integral is convergent. Okay, and similarly for the second case, limit x tends to 2, because 2 is singular point, so 2 minus x mu fx equal to limit 2 x tends to 2 fx, so 2 minus x mu fx यानी log x upon 2 minus x. So again here if we put mu is equal to half, then this should be finite. Otherwise problem to calculate the limit, because log x is here, so it is very easy. For mu is equal to half, this is finite, means limit x tends to 2 minus x half log x upon 2 minus x. So this should be cancelled, and this is log 2. Okay, which is finite. Again here mu is equal to half less than 1, so this is convergent. Okay, so first integral is convergent, second is convergent, so whole integral is convergent, means given improper integral is convergent. Okay. Now next test is comparison test. So what is comparison test? So let fx is a positive function and mod phi x less or equal to fx, then a to b phi x dx is convergent if a to b fx is convergent. Okay. Also, if mod phi x greater or equal to fx, then a to b phi x dx is divergent if a to b fx dx is divergent. Means if small thing is divergent, so greater thing is also divergent, and just reverse, if greater is convergent, then small is also convergent. Okay, so this is comparison test. Next important test is Abel test. Okay, so what is Abel test? So if a to b fx dx is convergent, means Abel test is also applied for product of two function. Means if we have two function, so first function is convergent and second is bounded and monotonic. Okay, then integral a to b fx phi x is convergent. So in Abel test, when improper integral of second kind contains two function, product of two function, then we use Abel test. So here one function is convergent and another function is monotonic and bounded. Okay. And similarly Dirichlet test, means Abel test and Dirichlet test used in same questions. Now Dirichlet test. So if a to b fx dx is bounded and another function phi x is bounded and monotonic, converges to 0 as x tends to a, then a to b phi x fx dx is convergent. Means if fx and phi x, two functions, so one function is bounded and another have three property. Three property means one is bounded, monotonic, and as x tends to a, this is 0, then product of two function is convergent. So Abel test and Dirichlet test used in product of two functions. Okay.